Hello everyone, we'll be discussing in this session consistency limits or Atterberg limits. So these are nothing but index properties of fine grained soil. There are other index properties also, but this particular index property is for fine grained soils in particular. Okay. Now, what are these consistency limits and then what is meant by consistency? We'll see. Consistency is the relative ease with which the soil can be deformed. When you add water to the soil, obviously the soil becomes a completely different material. It may be a plastic, maybe watery, right? So that ease with which you deform the soil in the presence of water is known as consistency. Now, what is consistency limit? It so you should make, I'm sorry, very clear in the mind that limits, consistency limits means these are nothing but water contents. Yeah, I will write it here. So consistency limits or Atterberg limits are nothing but water contents. We have represented water content as W. Now which water content? If you just see here, there is a dot here, there is a point here, there is a point here. Along this horizontal axis we have plotted water content, but these particular boundary water contents are known as consistency limits. We'll go into the details of all that, but before that you should have a bit of idea. That's why I'm telling you. So what is consistency limit? It is nothing but boundary water content. Now what is water content? You know, again I'll write the definition over here. Water content represented by W has a definition something like this: weight of water divided by, or mass of water divided by mass of solids or weight of solids. Okay, so that is nothing but water content. Okay, now which water content, boundary water content, is known as consistency limit. What is meant by consistency? It is the ease with which the soil can be deformed in the presence of water. Okay, further we'll read. It is applicable to fine grained soils. I have told you. For coarse grained soils means when the particle is larger, like sand or gravel, you cannot mix the water and then make it into a paste, right? It will not be a plastic. So consistency limits or Atterberg limits are not defined for coarse grained soils. Obviously they are defined for fine grained soils, right? It depends upon the water content. Fine. Now relative consistency can be expressed as, in descriptive words, very stiff, medium stiff, soft and very soft, with increasing water content. As the water content increases, it becomes softer and softer, and then as the water content decreases, it becomes stiffer and stiffer. So that is how relative consistency is described in terms of words. Atterberg is the person who defined these limits. He, namely, actually, he recognizes four states of consistency, namely liquid state, plastic state, semi-solid state, and solid state in clayey soils. Clayey soils is the particles which are nearer to the size of 0.002 mm or 2 microns with changing water content. Okay, he set arbitrary limits for these states and called them as consistency or Atterberg limits. And these limits are most useful for engineering purpose in order to classify the soil. Now, what are the Atterberg limits? They are liquid limit represented by W with the suffix L, plastic limit W with suffix P, And shrinkage limit, W with suffix S. W stands for water content, and then L liquid limit, P plastic limit, S shrinkage limit. Now in short, if you look at this graph where there is a volume versus water content, the water content is large here, corresponding to say the point A. We got a lot of volume of water. Now you can just see here in the figure also it is shown, that is soil is there, soil solids are there, a lot of water is mixed. So obviously here the volume is quite large, and the ratio of weight of water to weight of solids, that is water content, is also quite large. Now when you go on drying it, what happens is water is decreased. Now as you go this way, water is getting decreased, but solids, weight of solids is remaining the same. In this ratio of water content, Ws is maintained the same, weight of water is decreased. When a weight of water decreases to 0, water content becomes 0, but weight of solids will be there. You can just see this brown color. Weight of solids all along this discussion will be remaining the same. What is changing is the weight of water. Here it is quite large, it is decreasing, and ultimately when it comes over here, the water is completely 0, and then voids are completely filled with air. Now we'll continue our discussion. When you add a lot of water, it becomes muddy water, or a soup kind of stage. Means when you have a lot of water mixed with the solids, obviously it is a muddy water, right? So it will be flowing, it will be liquid state, it will not be having much of shear strength. You know that the fluids are defined as substances which have negligible shear strength. The solids are the one which will be possessing shear strength. Because of that, they cannot flow, they will not be flowing, right? Now here, as the water content decreases, the soil behaves, which is behaving like a liquid, stops behaving like a liquid, in the sense it will not be flowing. The limiting water content up to which it acts as a liquid is known as liquid limit. So this particular point represents liquid limit. Let me write that. So here, so it is water content, but it is liquid limit with a suffix L. Now if you have water content here, it will be flowing, but this particular water content is a boundary water content. You can just see here boundary. This will be in liquid state, it enters into a plastic state. This boundary water content is known as liquid limit. Means if the soil possesses a water content lesser than the liquid limit, it will not be behaving like a liquid, but it will be behaving like a plastic material. It is nice to play with, make models out of it. Now as you go on decreasing further water content, you can just observe here at point B there is some volume of the soil, means the water as well as soil mix. As you decrease the water content, volume also decreases. There will be a point C, corresponding to that, or the volume is over here, and then here there is a water content. This particular water content is a limiting water content, wherein it acts as a plastic material. If you have a higher water content, it will be plastic, but if you reduce the water content less than this, it will not be behaving like a plastic. So this particular water content corresponding to this point is known as plastic limit, P, WP. Now it enters into semi-solid state. Now here, as you decrease the water content, here what is happening is volume is decreasing, right? Now volume is decreasing, but you cannot make the volume of water soil combination completely 0. You can imagine that water content can become 0, When it becomes 0, water content definition is weight of water to weight of solids. Now weight of solids we are maintaining the same. You can just see these brown particles of soil. Weight of water can be reduced completely 0. So when weight of water reduces to 0, water content becomes 0. This is the point. But though the water content is 0, there will be some minimum volume for the soil, and that is represented by this horizontal line. So again, coming back to the point C, as the water content decreases, the volume is decreasing, but a particular point or a stage which is represented by the point D, here the water content is decreasing but the volume is not decreasing. So such point is known as shrinkage limit. So the soil stops shrinking in its volume. That's why this particular water content is known as shrinkage limit, and it enters into solid state. Okay. This is also a very nice representation where when the soil is with very little of water, it can be a candy kind of consistency. When you add the water, it can become cheese. If you add little more, it will be butter plus, and then it will be in plastic state. If you add little more of water, it will not be a pasty thing, it will be a watery. That's why it will be in soup state. We say that this is in liquid state, and then from this particular level to this we'll call it as plastic state, and then afterwards it enters into semi-solid state and then solid state. So whenever we want to discuss about consistency limits or Atterberg limits, we have to make use of this particular graph, a very important graph wherein volume is represented by vertical axis and water content is represented by horizontal axis. Right, there are 4 states: liquid state, plastic state, semi-solid state and solid state. The boundary water content between plastic and liquid state is liquid limit. The boundary water content between semi-solid and plastic state is known as plastic limit. The boundary water content between solid state and semi-solid state is known as shrinkage limit. Okay, we'll go further. Okay, here I have defined liquid limit. The words are like this. Liquid limit, it is the water content corresponding to an arbitrary limit between liquid and plastic states of consistency of the soil. It is a minimum water content at which the soil is still in liquid state but possessing a small shear strength of the order of 1.76 kilonewton per meter square and exhibiting some resistance to flow. There are 2 methods for finding liquid limit. One is Casagrand's method, another one is cone penetration method. We'll be seeing both these methods in detail. In Casagrand's method, there is a Casagrand's apparatus. Right here, this is made up of a hard rubber base. There is a brass cup. There will be arrangement over here such that when you rotate this cam, this will be lifted up and dropped. There will be adjusting screws. This particular pad is having a height of 1 centimeter, which will be used for calibrating height of fall. It will be adjusted for 1 centimeter or 10 mm of fall, and this is known as grooving tool. Casagrand's grooving tool. You have to fill the soil and make the groove. That is what is the point here. We'll go into the details of this. In cone penetration, the soil paste is filled in a brass cup, and then a particular standard cone is brought up to the surface and then let to go fall on its own mass or weight, and then if the penetration is exactly 20 mm, corresponding to that whatever water content you have, that will be defined as liquid limit. Okay, we'll go into the details. So liquid limit by Casagrand's method. Here there is a equipment. Here there are two grooving tools. One is called Cassegrain's grooving tool. There is one red and then one white. Both of them are Cassegrain's grooving tool. This particular one is ASTM tool, American Standards for Testing Materials. So here there is a groove making arrangement. Here there is a arrangement of 1 centimeter height, so that you can adjust the height of fall, height of drop as 1 centimeter. Now we'll go into the details. A required amount of soil passing through 425 microns is mixed with water until a uniform consistency is achieved. So you have to make a paste of the soil. The liquid limit device is calibrated such that the height of fall is 10 mm. The soil is taken into the cup such that the surface of the soil is parallel to horizontal. You can just see in this sketch, the surface of the soil has to be horizontal. Here also you can make out, here also you can make out that the surface of soil is horizontal. Not the soil is fully filled like that, but it will be made like that. Okay. Then using a grooving tool, the soil is taken out such that the grooving tool is always perpendicular to the cup at the time of contact. Means when you hold this here, it has to be perpendicular to the surface. Means when it is over here, it will be like that. When it will be here, it will be like that. When it will be here, it will be like that. Means always the grooving tool has to be perpendicular to this surface. That's how the groove is made. The groove will be having 2 mm at the bottom and then around 10 to 12 mm at the top. Such a groove is made. Now, the drops are given such that the handle revolves at 2 revolutions per second. So when you revolve the handle, it will be lifted up and dropped. The speed at which revolutions are given is 2 revolutions per second. The number of blows required for the soil to join the groove is noted and the sample is taken for moisture content determination. Now, the rotation is done or the drops are given till these two halves of the soil come together for a distance of 12 mm. When they join through a distance of 12 mm, we say the groove is closed. Till that we have to give number of blows and stop the number of blows and record the number of blows, and some sample out of it is put for water content determination. So you will have you can just have a look of this graph. Here there is a water content, here there is log of n. It's not properly printed. Let me write that. So here we have log to the base 10, so log and then n is number of drops. So a point over here represents n is the number of drops required, and corresponding to that the water content is so much. So that is what the idea is. So when you test with particular water content, you will have n, the number of drops required for closing the groove, and corresponding water content, so that you will be getting 1 point in the graph. Now you increase the water content, redo the experiment, and then you may find, now when you increase the water content, we are going on this axis in this way. The water content is increased. As the water content increased, the number of drops required to close the groove will be obviously less. So the second point may be over here, third point may be over here, right? Fourth may be here, fifth may be here. Like that, you will be having a number of record points wherein number of drops required and then water content will be known to you. Only care has to be taken that the plotting is done on semi-log graph. This graph is on the x-axis. You got a logarithmic scale on which n number of drops are plotted, whereas water content is plotted on uniform scale. Okay, Here, best results are obtained for blows ranging between 15 to 35. If you are having number of drops less than 15, better you add bit more of water. And then if you are going beyond 35 number of drops, then better you add the soil so that it becomes a bit dry. Now finally, what is liquid limit? The water content at which the groove cut in the soil paste will close upon for 25 repeated number of drops of a brass cup is designated as liquid limit. So you got number of points. Now what we should search for is, you go for 25 number of blows, go up, you reach the curve and then search for the water content. Whatever water content is there, that will be designated as liquid limit, LL or WL, so much of percentage. So that will be the liquid limit by Casagrand's method. Okay, here we have fall cone method. This particular method is developed by Transport and Road Research Lab, UK. Okay, now here also the soil taken is passing through 425 microns. A bit more of soil is required because a big cup of soil has to be filled in, right? Now there is a standard equipment wherein this particular cone with a rod and then a pad etc. will be having a standard mass, a standard geometry. Now after adding some arbitrary percentage of water, you fill it properly, make the top horizontal perfect, and then put it below. Bring this exactly to the tip, right? The cone tip is brought into contact with the soil surface and the time is initialized. You have to just start the stopwatch. The cone is released for free fall. At the end of 5 seconds, penetration is recorded. Means after 5 seconds, whatever penetration is there, which will be read from here, it will be recorded. The water content corresponding to a 20 mm penetration is designated as liquid limit. That is what is the definition as far as fall cone method. Corresponding to 20 mm penetration, whatever water content is there, that will be known as liquid limit. Since the water content for the penetration depth of 20 mm would be a chance occurrence, obviously it will not be possible exactly to get 20 mm. Several trials at different water contents on both the sides of 20 mm penetration are used to construct a plot of penetration versus water content. What it means is, you have to have a plot wherein number of or extent of penetration, let me represent it as X, and then here water content, right? As the water content increases, the penetration also increases. Because of that, the graph will be a straight line, something like this. Now penetration is say 20 mm at this particular point. Now when you go up the line, you will be getting a point, and then you have to go to the left, and this particular point will be giving you a liquid limit, right? So when you mix the water, you may not get exactly 20 mm penetration. So this is 20 mm penetration. You may be having little less corresponding water content, you can just put a point, and then little more of penetration corresponding water content. So like that you can have number of drops, have a curve, have a straight line curve, and then afterwards search for 20 mm penetration, what is the water content, and that will be known as, this particular point will be known as liquid limit. That is what this means. The care is taken every time that the penetration is in the range of 14 to 28 mm. Okay. Now next is plastic limit. It is a simple experiment. The definition goes this way: it is the water content corresponding to an arbitrary limit between plastic and semi-solid states of consistency of the soil. This you have seen in the first slide only. It is a minimum water content at which the soil is still soil will just begin to crumble when rolled into a thread of approximately 3 mm diameter. The soil is made into a ball and then it will be tried to roll it into a thread. The size should reach 3 mm, and then if you want to go below 3 mm, it should crumble or crack down. Then you can just lift up this particular soil and then keep it for water content. Whatever water content that you get, that will be known as plastic limit, right? So plastic limit, that is this point, is nothing but the water content, boundary water content between plastic state and semi-solid state. How to find out? You have to take the paste of soil, try to roll it. If you are able to roll it below 3 mm, then the water content is more. And then while rolling, if you are not able to reach up to 3 mm, then the water content is less than the plastic limit. That is, you are in semi-solid state. If you are able to roll it less than 3 mm, you are in plastic state. So it should so happen that when you roll it, when it reaches 3 mm, it should start to crumble or crack down. Such water content, when the soil is rolled into 3 mm, it starts cracking. The corresponding water content is known as plastic limit. Okay, we'll stop here. We'll continue afterwards.